Okay, welcome to our lesson on the equation of lines in R3, or the equations, so the different forms of the equations of lines in R3. So for this one, I'm going to assume you've already watched the video or been in class for the lesson on lines in R2. So we should know the following in R2. We know about slope y-intercept, y equals mx plus b, Cartesian or standard or scalar form, ax plus by plus c equals 0, and then the ones we've learned, vector, parametric, and scalar. So now we're going to talk about which ones of these generalize to R3, or 3 dimensions. Okay, so to start with, slope y-intercept. Does slope y-intercept generalize to R3? Well, the problem is slope, right? M. Does M have, can you find the slope in R3? And the answer is no, right? Slope is equal to M equals rise over run, but so that's good enough in R2, right? Because you only have 2 dimensions. But in R3, there's 3 dimensions, so rise over run, and then you need a third one, and obviously you can't write that as a fraction. So this one will not work in R3. Okay? How about Cartesian? Well, again, remember the ax plus, or the a and the b were just the normal vector. Well, in R3, any line, I can't really draw this in R3 because it's R2 that I'm drawing on. But there's going to be too many normal vectors, right? That's normal, and then like it could be coming out of the page. That would be normal. The one down here would be normal. There's sort of infinitely many. You could just take this line and then rotate it towards yourself. So there's infinitely many normal vectors. So you can't have a Cartesian equation either. It won't work. Vector equations, well, we do have vectors in R3, so vector equations will work. Parametric equations will work because they're really just vector equations. And scalar equations are also going to work. The only thing that's going to be different about these is we'll add a z, or the third component. Add a, I'll call it z. Component. Okay, so we'll work through an example, and I think that will actually, make it, that's all we'll really need. It should be fairly straightforward, actually, as long as you understood the lessons on R2. Okay, so let's say we have a point A, my favorite point, 1, 2, 3, and B, let's go with -3, 1, 2. So we'll, part A, find vector equation. So same deal as in R2. The first thing you need to do is find the direction vector. Okay, so find the vector in the direction of this line. Well, that's just as easy as it was in R2. I guess not just as easy, it's 50% more complicated because you have an extra component. So what all you have to do is figure out the vector AB. So how do you figure out the vector AB? You take the b's and minus the a's. So -3 minus 1, 1 minus 2, 2 minus 3. So that's equal to -4, -1, -1. That's our direction vector. Now if you don't like the negatives, we know that any multiple of this vector will work. So I'm just going to take -m, 4, 1, 1, just a little bit easier, nicer to look at. So that's my, better do this all up here, that's my direction vector. So my vector equation will be x, y, z, which is r, will be equal to a point on the line. Well, which point should I take? Sure, A. Could have taken B. So 1, 2, 3 plus t times the direction vector, where t is a real number. Okay, so vector equation of a line. That simple. If I wanted to change this to find parametric, So in R2 we had two parametric equations for a line because there was two components, x and y. Now we're going to have three. So x will equal 1 plus 4t, so all the x components, 4t. Y will equal 2 plus 1t, or just t, and z will equal 3 plus t again, where t is a real number. So that's your parametric equations. That's simple. And now let's say we wanted to go to symmetric equations. This one's very much the same. So if you remember what we did for symmetric equations, we solved for t, although there was only two equations, but now we'll just do it 3 times. So we'll have x minus 1 equals 4t, so t is equal to x minus 1 over 4, so that's from the first equation. The second one, y minus 2 equals t, so we've got t equals y minus 2, that's the second equation. And then the third one, z minus 3 equals t, so t is equal to z minus 3. So we have these three equations, they're all equal to t on the left side, so we can set all the right sides equal to each other. So x minus 1 equals 4 equals y minus 2. And now this isn't written like this, but I'm going to put it over 1. And if you remember in R2 why we did that, you'll know why we're doing it in R3. So I have these equations here. These are my symmetric equations. One question I might ask is, how many equations do I have here? In R2 we only had one equation, right? We had x minus 1 equals 4 equals y minus 2 equals 1. And that was it. There wasn't this part, so it was just one equal sign. So how many equations are there? So how many symmetric equations do you have for a line in R2? You might see two equal signs and say, okay, well, you might say there's one. There's just one thing written there. But there's actually two equal signs, so there's more than one. There's actually 3 equations, right? We have 1 equals 2. That's one equation by itself. We then have 2 equals 3. But there's also this sort of long equation, 1 is equal to 3. So there's actually 3 symmetric equations for a line in R3. Alright, so just to generalize that, how did we get these numbers 4, 1, 1? Well, you should recognize that's the direction vector, same as in R2. And how do we get these numbers 1, 2, 3? Well, that was the point. So if x, y, z is a point on line, and is a direction vector, so this is now all in R3. Then our symmetric equations are, you know what, I'm going to call this x1, y1, z1. So we'll have x minus x1 over m1 equal to y minus y1 over m2 equals z minus z1 over m3. Okay, so those are the 3 types of equations we have that for lines that work in R3. Okay, so, and then everything we did in R2 we can now do in R3, so the same types of equations. I won't go through lots of examples because it's the exact same thing. It's a little bit more work because of that extra variable t, but same deal.